Okay. So next we will learn this template. So template, for learning this template, we have the example stack. So we already have this when we learn design patterns. So we have this stack, and then this stack stores integers. And what happens if we want to store float? And then we have another stack, right? We have to write another stack. So another example is that we want to sort an array of values. Actually, this is integer values. We have this bubble sort algorithm. There are 2 for loops. So we have to compare between the 2 elements. Then what happens if we want to compare float values, float arrays? Then we have to write another sort function. Basically, most parts are similar, and we can we only modify this, right? Modify this input, right? This input to float. So we may think of ways. Is there a way to avoid this kind of redundancy, right? Or not? Right? The problem is that stack and sort can only be used for one type of data. For different types of data, similar versions of stack and sort are needed. So there are a lot of code repetition and redundancy. How to avoid this? How to avoid this? So CPP language provide us with a template. So this is template is to avoid this kind of redundancy. So this is the way to write the template, function template. Right? So we have this keyword template, and we have the type to represent any type. This can be built-in type, int, float. It can also be a class, right? Can also be lambda function, right? Can also be lambda function, right? Like that. So this is template. So now we can sort different function, different types of array. Then we can other things are different, are similar, right? This part of the code are all the same. So we only have to modify this and this, right? So this is how we write a function template. So a function template is a function without type. Function template is a function without type accepts different types of arguments, right? So this is a keyword, and this is the how we write it. So this one is represent data type, and so on. Okay, let's stop here, and first we will ask our TA to share something on our exercises, and then we have in-class talk. Okay, let's start our class today. So in our last class, we have learned the, actually we started beginning of template. So we learned to this function template. So actually a function template is a function without type. So that means, so this function template can accept any type, right? So you can provide type here. Then your function accepts any type of parameters. Okay, and the instances of function template are generated after compilation. After compilation, there's no template. There are some instances of functions. Okay. So this slide shows how to use function template. So when we define a function template, for example, we define the sort. Actually, function body is the same. We only change the type of the parameter.
or argument. And then when we call the function in this way, so this is the grammar for calling this function template. We provide the type as a parameter in angle brackets. Then the compiler will generate, during compilation, the compiler will generate a function instance. Right? The function instance is like this. Right? So the compiler will do that for us. We have a function instance here. And then the compiler will call this function instance generated by the compiler. Right? So, and this is how to use function template. Okay. There's also another way, an implicit way of instantiation for this one. So we just call sort. So the compiler will check the type of L. It will try to deduct the type of L. So the compiler can check. So finally, it can obtain the type of the L within an array of integers, right? Then it knows, okay, now t is int. Then the compiler will again generate the function instance. Okay, and then we'll call the function instance. So this is the implicit way. So now we have a question. So we want to sort character string by alphabet order, dictionary order. How to do that? So if our function template for sort is like this, so we want to compare two elements in the array. Now the elements are character strings. Does this comparison work or not? So this is the question. Actually, for this character string array, if we want to sort them by this function template, it does not work. So this is the result. Yes, sorry about that. So this should be const. Okay. This should be const. So if we sort these character strings, then if we just use this comparison operator, then it will sort the strings by address. So the address in the string, this one is smaller, right? This is greater, this is even greater, and then this is largest address. So the result is 1, 2, 3, 4. This is not alphabet order. This is not alphabet order. It's not dictionary order, right? So how to do that? How to sort it? Sort the character string by dictionary order. So we need a special way to solve this problem, right? So actually for character strings, we cannot use this operator, right? Cannot use this operator. And for character strings, the sorting function is kind of special, right? Because originally for other types, we can use this, right? For general types, we can use this. However, for character strings, it is special, right? It is special. So we need to use string camp. So this will compare the string by dictionary order. So to solve this problem, we introduce template specialization. So template specialization is to define special cases for special data type. So this is how to use template specialization. So basically we have two function template. This is one, this is two. So this is for general types, for integer, for float, like that. Then this is a specialized template without parameter, without a type parameter. So we directly use this type here. Then we can sort it. Then we can sort it. So that means we provide two templates. One template is for general cases for all other types, and one template for special cases, for one special case. So this one special case is for character string, and we use string camp to compare it. Then the compiler will smartly compare this. Okay. So the results is like this. If we define this general template and the specialized template, then when we use sort here for character strings, then the compiler will smartly determine, okay, we need this template. Then we get your correct results, sorted in alphabet order. Okay. There are some other examples. For example, for realizing this to get the minimum one, so there are function ordering ways and macro ways, and we also have these template ways. Actually, this is a standard function, right? We can directly call the standard function. Anyway, we have different ways to do this. There are also lambda expressions to do this, right? And there are some grammar issues with this template. So the types identifier cannot be duplicated. So we can now say, okay, we have two class T. This will get an error. However, we can use one type for two parameters, like this. This is correct way, and this is the wrong way. We can use one type for two different parameters. And each type identifier should appear in the function parameter list. If we have a type identifier here, T, but it is not used in the function, then it will generate an error. Then for this function template, I have already learned that. And then we know that an instance of function template is a function. So actually, during compilation, the compiler will check the type of the array, and when the compiler determines the type, it will actually generate an function, right? Specialized function, right? for this function call. So this is an instance of function template. And for a class template, instance of a class template is a class. So when we define a class template, this class name, this, then we can use a class name some type, right? Int, for example, float. This, I think most of you have already seen this, right? Because when we use STL template, right? So we always do this. We are providing types. So now with this angle brackets, we have a class. So this is actually a class. This is class. Okay. Type name and class can be used interchangeably. There's no difference actually. So you can use type name and you can also use class. Okay. Then this is for our original example, we have the stack. So we have an integer stack. Now we want to generalize the stack to different types. Then we can define a template class like this, our class T. So now we can have the other parts are the same actually. We only need to change this. Right? We only need to change this. And also this. Okay, so this is a template class stack. Okay. This is how we use the stack. So we have to provide angle brackets with a type. Then we have an integer stack. And then using this, we have a float stack. We can also have a string stack. Okay. And this is a graph showing the instantiation of the class template. So when we define the class template, if we have different types, when we define different types, then actually we will have different classes. So this is a class, this is a float class, a float array, and this is an integer array. There are two classes. Then using the two classes, we can define different objects. And these are the objects. Okay. So after learning this template, we just regard this is a very special way of writing a class. That should be easy for understanding. Okay. So when we if we regard this as a class, then it is easy to understand. For example, if we write a subclass, class sub, that is for example is array float. So we can do that. So we can write some, some subclass of this kind of class, right? Okay. And Okay. Also, the templates should be defined in the header file. There should be some semicolon, right? I think there should be some semicolon here, right? This is CPP grammar, right? Then typically all the templates are defined in header file. So this is a rule, and I think this is some shortcoming or some constraints on template, because the header files, we always provide header files if someone wants to use our code. So if we want to, originally we have class, we define some class, and then we provide the function bodies, member functions of the class in the CPP file, right? And then we compile it into .o, and then we add it, archive it into a library, right? Then in this way we can kind of protect our intellectual property, right? However, if you use template, if you want others to use your code, you have to provide your header file, and all the template implementation is in the header file. So, and there actually is no way to protect your intellectual property. So this is some constraints on template. There's also some other grammars on template. For example, we can use built-in types as arguments in the template definition. So typically it's integer, either int or unsigned int, long, other types that can be casted into integers can be used. So during compilation, such types are instantiated as constants. So now in the template definition, we have an integer parameter. Right? So this is class T, this is type name T, and this integer parameter. Right? And then after compilation, this will be a constant. This will be a constant. This gives us the size of the stack. How many elements can be stored in the stack. Then we will use it in this way, right? In this way. So we provide an integer here to limit or constrain the size of the stack, maximum number of elements in the stack. So this will be passed into the template as a constant. So we can imagine that the compiler will generate a class instance in this way, right? In this way. Class stack, and then this is the T. That's right. And data, and this should be some variable, right? Maybe what I can imagine it should be for example, it's x, and then should add some const static x, or you can remove this static. Right? You can just use const x. Right? Then this is x. Right? It's possible. Any suggestions? I think this static may not be omittable, right? So we should use static here. Otherwise, we cannot define such an array, right? Then this X will be initialized in the constructor of this class, right? The constructor of the class. And then we can define, anyway, the compiler should initialize this const static member, right? Then it will have the fixed size array for this stack, okay? Anyway, this is my imagine. This is my analysis and understanding. Anyway, the compiler should have a way to do that, right? Should have a way to create an instance of this class template. Actually, it should be another class, right? And the template parameter can have default values. So in our previous example, we can have this, and also for this type, we can have this. This is a default type, and this is default size of the stack. Then we can use the stack in this way. We do not need to provide a type. Then by default, it is an integer stack. And the size of the elements is 10. Okay, and this is default value. We have mentioned that we can define a subclass of a template class, right? So this is a way. This is also actually this is a template class, and actually we can define subclass for this, right? So this is a template class list, and then this is how we define a sortable list in this way. However, we mentioned that in our previous slide, our example is like this. We can define a class, right? For example, S list. That is we can define in this way, actually. So this is another way, because we have mentioned that anyway, this list int should be a class. So we define a subclass of int list that should work. We can also have this way. So this is to define a template subclass, right? Template subclass. Then this class T is used both in list and sortable list. Right? This type T is used in the two classes. Right? So this is how we do inheritance of for template class. Inheritance and composition could reuse object code. We have mentioned that, right? Only header files and libraries are needed. However, template, we use source code for different data types. So for users, source code of template is needed. So in this way, we have nothing to protect. There's no way, right? And the compiler makes sure to generate each template instance only once. So we mentioned that during compilation, for each template, compiler will generate an instance, right? Either a class or a special function. And if there are different places for the same function call, then the compiler will call the existing one. Right? It will not generate two functions with the same parameter type. And this slide shows template template actually provides some kind of polymorphism. That is compile time polymorphism. So this is template. After compilation, we have this version, this version, this version. If we have this function, corresponding function calls. So this is kind of polymorphism. Right? So from our code reader, code designer, it seems that one piece of template code can be used for different data types. Actually, compiler will generate multiple definitions, actually. And we have learned this word polymorphism. We know that the polymorphism, the idea from inheritance and virtual function is like this, right? So from the user sees abstract class, and then during runtime, polymorphism works by function behaviors. Different class instance will correspond to different function behavior and output. So this is virtual function with this real polymorphism. Now for template, there is some kind of compilation time polymorphism by the data types. There's something to note with template and derived class. So we can create a new template class by inheriting an ordinary class. So this is another way. Right? We have mentioned that we can define a template class, right? Template subclass, right? Of a template class. We can also define a template subclass of an ordinary class. That's also possible. Then we can inherit this instantiated template class. Right? This is another way. Right? We have mentioned this. Right? Because an instantiated template class is an ordinary class. Actually, they are equivalent to each other. During compilation, instantiation of a template class or function generates a new copy of code. So if there are different function calls with different data types, then there will be many versions of the code. Then this will cause increase in the size of the code. So this code corresponds to the executable code. So the size of the executable will be increased a lot. So this will kind of slows down the compilation time. Our suggestion is that we should try to make templates more condensed. Try to avoid codes that are not directly dependent upon template parameters. In this way, we can kind of reduce the size, right? Reduce the size of the executable code. Okay, so for example, we can make a base class for these independent codes, right? So because this base class, there's no data type, and this is not a template class, so there's no different copies of these independent codes. So only those codes that's dependent on template parameter, then we need to make different copies. right? Then in this way, we can kind of reduce the size of this code. Okay, so this is a template and derived class. Template makes an algorithm or a structure independent of data type. Right? So by defining template class and template function, we remove the data type. Right? So in this way, our algorithm is generic, right? It is applicable to different data types, right? Different data types. So when we remove the data type, we can work for any data type. So this is the key idea of template. Such an algorithm or structure is general or generic without a data type. And so in this way, template decouple algorithm data structure from data type. So in next semester, I think the semester after next, right? Next spring. Sorry, it should be next semester, right? 就数据结构我们是在下学期上的吧？应该是的。OK， great。我们下学期的数据结构我们就要用到这个。So template is very important for data structure. So when we learn this data structure, template will be very useful because our data structure should be useful for different data types. Right? We should be able to store different data types. So we always define data structures using templates. Therefore, generic programming is enabled, where we only focus on the algorithm or the data structure without caring about data type. This is very important for writing pure algorithms, pure structures. There's another question. So using our previous sorting function, the template sort, so we use this kind of comparator, this operator to compare different elements in the array. If we want to sort students, what will happen? So now we have students, 10 students, and we want to sort the students, right? Objects. How to sort it? Does it work or not? This is the question. Does it work or not? For example, we sort by student IDs. Actually, it does not work. So if we want to make it work, one way is to write a template specialization. Yes, very great answer. This is our solution, and we will mention about it later. We need to overload. We need to overload this comparison operator for students. So one way to solve this, actually, and this is one way, template specialization. We just define a specialized template, especially for this student object. So this is one solution. Another way is to make it work, make this work for students. How to make it work? We should make students comparable, right? How to make students comparable? We need to overload this operator. Right? Need to overload this operator. So whenever we want to make some objects comparable, we need to think about this. Right? We need to think about overloading the comparison. This one. This is a comparison operator, right? And this is stream operator. Whenever we want to make objects of classes to be comparable, we need to think of overloading the comparison operators. In this way, we can sort them. Okay? Using a generic sorting algorithm, we can sort the objects. Okay, and this is how we test students. We can sort students. Okay, then that is the basic grammars and usage of template. Actually, I suggest all of you to read the book and learn more about template. I think these are enough for basic usage of template. And I also want to mention something about this meta programming, because this is also interesting with template. So meta programming is compute during compilation. Compute during compilation. So in this example, we have this template, this factorial template. So actually, we provide a built-in type here, right? So in this case, we can provide a constant, right? Compiler will pass a constant into this template. However, because we have this specialized template, during compilation, the compiler will recursively call the template so that it will compute the results out. So during when we run the program, it will directly print the results. So this result is already computed after compilation. So this is a very initial taste of this meta programming. If you have some interest in this, you can explore more how to use compiler to compute. Okay, and this is for template. Actually, because we have this GitHub submission, and also we have, I think there are also some other works to do. So for this mandatory exercise, we may not provide too many exercises for you for now. However, instead, we will provide homework, examination problems in the previous year. 就是我们应该会我们这个应该会给大家提供一个往年的这个期末考试的上级考试的题目供大家练习这样的话呢，我们将来上级考试的时候呢，也大概知道大概有什么样的类型